So the last thing that we looked at this lesson was the fact that pH is equal to a negative log 10 to the hydrogen ion concentration. So how did we discover that? That it was a logarithmic scale. So it was to the base 10. Is that pH changes by, we said 1 for every power of 10 change in acid concentration or the hydrogen ion concentration. So where does that bring us to? We just want to go back and have a look at where does this idea of pH come from? How did we get this pH scale? If we can imagine now a beaker of water and you've got all of those little molecules moving around and flowing about and they're doing, their thing, they're bumping into each other, all that sort of stuff. Every once in a while, to a small but measurable degree, one water molecule that has bumped into another water molecule will actually release its hydrogen ion, or will release a hydrogen ion, okay, out of the two possible hydrogens that it's got. This will form a hydronium ion and a hydroxide ion. And I'm going to skip all of this. You can read this yourself. Just talking about the square brackets and why we use them again. If we look at laboratory conditions, standard laboratory conditions, that at 25 degrees Celsius, there are 1.0 times 10 to the power of negative 7 hydrogen ions per liter of water, okay, per liter of solution. There are also 1 times 10 to the power of negative 7 hydroxide ions, or moles per liter, rather. Okay, there aren't that many of them, but there are that many moles in every liter of water. So if we use our pH equation that we've just looked at earlier today, the pH will be negative log 1 times 10 to the power of negative 7. Where did we get that? We got that from here, the hydrogen ion concentration, okay, from here, in water at 25 degrees Celsius. If we plug that into our calculators, you'll get an answer, hopefully, if your calculator's working, of 7. So this is where our pH of 7 comes from. Neutral. That in water, there's this idea of self-ionization, that water will ionize with itself. Not often, but just enough so that there are 1 times 10 to the negative 7 hydrogen ions. Hydrogen ions, that's the concentration, okay, moles per liter. If we keep moving, we can also do the same thing for hydroxide ions, and we call this POH. We haven't heard this, probably, we haven't heard this before, but it can become very useful, and it's exactly the same as pH, but it calculates POH by using hydroxide ions. So likewise, our POH for water, if we're looking at the same example as before, is negative log 1 times 10 to the power of negative 7. POH in water is 7. Okay, therefore, we're going to come to a point here. Therefore, if we add the pH of water, 7, if we add the POH of water, 7, that gives us our 14, which is our magical number of our pH scale. It goes from 0 to 14. So that's where we're kind of getting that from. If we continue on, we'll look at a couple of examples that I want you then to continue on for homework. We can also work backwards. So we can calculate hydrogen ion concentration from a given pH because we know it's a power of 10 scale. So hydrogen ion concentration, therefore, is equal to 10 to the power of negative pH. And that's how we would work out what the hydrogen ion concentration would be. If we have a look at a couple of examples here, we'll do one together. So we're calculating the pH. So therefore, I write my equation, okay, as per normal. We always start with the equation before you actually input any data into it. So pH is therefore equal to negative log of, here's my value, 1 times 10 to the power of negative 6. pH is therefore equal to, you plug it in, it should be 6. Note that this has a 10 times more concentrated, or the hydrogen ion concentration is 10 times that of water. So it's 10 times more, hence the pH being 1 factor less, okay? If we have a look, and we'll do 3 just to show you what's going on with the working backwards. If we're trying to work out the hydrogen ion concentration, we simply plug into our calculator 10 to the power of negative pH. So we write our equation yet again, and then we input the values. So 10 to the power of negative 2.68. You plug that into your calculator and that will be our answer. Now that will be our answer in moles per litre. Okay, so units are important. pH actually doesn't have a unit. So because it's a relative scale, okay? So no units. pH is just a number, okay? It's a relative number. Concentration always has units. If we calculate, or rather, if we calculate POH, we can also find pH of a solution. So remember, we said pH plus POH is equal to 14. If we look at number 1, okay, the POH of a solution whose hydroxide ion concentration is 1 times 10 to the negative 11. So they've made these ones pretty simple for you to do. So let's do 1. POH is equal to negative log to the hydroxide ion concentration. So therefore POH is equal to negative log of 1 times 10 to the power of negative 11. That should be, correct me if I'm wrong, 11. If we then wanted to work out what would be the pH of this solution, so this POH is 11, we would look at our equation and we'd go, okay, so I've got POH, I want to work out pH. Would it not be 14 minus the POH? So I've just rearranged this above equation. What is that? pH is equal to 14 minus 11, so therefore the pH equals to 3. So this is an acidic solution in this particular instance. And then I could work back from there, and I could even say, okay, well, we've got the hydroxide concentration, but what's the hydrogen ion concentration? Well, it'd be 10 to the power of negative 3. So the hydrogen ion concentration is 0.001 moles per litre. Units, important. Okay, so you can do the same for all of these examples, and that's what I want you to do for homework. On top, I'll send you another worksheet in order for you to complete some more pH calculations.